So consistently this kind of evolution happened, right? And which evolution happened for what, that you can explore. That's a broad domain of course, there can be a separate course on that. But this kind of evolution happened consistently. Question again come, what will be the next? So what is the main challenge now? I'm explaining you what. So what if you, let's think about the material. This is a standard silicon material. So if a standard silicon material earlier it was, and if carrier has to flow, then earlier carrier was flowing into the bulk. If carrier was flowing into the bulk, all sides had a standard bonding. So there was no significant problem in flowing the carrier. If you used to read about a standard crawling penny model and a standard device physics, then if material is pure, then carrier will not have problem in flowing into this. But if you thin down this complete system, if you thin down the complete system, then what will happen? Surface has the damming bonds. Damming bond means some matter which is not bonded. Because if you see a standard silicon, if some silicon in the bulk is bonded with 4 different silicon atoms. Okay. But if some silicon on the surface, it's the topmost silicon atom, it's all orbitals is not filled, it's a damming bond. Right. So what happens is once the carrier flow through this, carrier can get trapped into those damming bonds. Carrier is flowing unbonded orbitals which they want to pick, so electron or hole can get trapped into those carrier. So electron or hole can get trapped into those carrier. So this is something a standard word in the device physics, which is known as surface and boundary scattering. Right? So means scattering is basically electron need to get scattered from the standard flow into the surface property or standard damming bonding. So what will happen if you shrink down consistently? Then it will make your surface and boundary scattering huge, and that will dip your mobility. All of them are standard mobility, right? So your mobility will get dipped down. Your mobility, and ultimately, if your mobility will get dipped down, your device will be slow. Okay, so this is there are many other problems, but this is the most fundamental problem. If you go for a scaling, so there will be limit on which further you cannot improve the scaling in silicon. If you see a different technology, they are doing something else, but they are not ultimately modifying the scale. Another problem is, if you go study about the quantum mechanics, then what you read that if you confine any system, confine means you are putting boundary conditions, you are confining the system, then what will happen? Your probability of finding the electron or carrier at edge will be less. So what happens? Carrier will try to be in the middle. Means maybe somewhere, it depends on which mode you are talking about, but carrier will go away from the edge. This is the thing. If carrier will go away from the edge, then what will happen? If you apply the voltage, then to control the carrier you have to apply more voltage. If carrier will be closer to the surface, then if you apply voltage on the surface, you can control the carrier easily. But if your carrier will go away from the surface, then controlling the carrier will be difficult. You have to give more and more voltage. Right? So these two are standard problem. It's other way. Mobility part, you try to keep away carrier so that you should not have more and more boundary or surface scattering. But if you keep away your carrier, then controlling of your carrier will be difficult because you have to apply more voltage. So you want it to be surround surface. So, and of course, then these are the standard problem, basically your mobility degradation and weak gate length. And of course, if you shrink down consistently, then some time will come that what you have to do, you have to silicon bond limit will be there at some point of time. So what would be the solution? Solution is you make your surface damming bond free, first thing, so that boundary scattering, especially surface scattering, should not go away. Second is go to very thin atomic scale thickness. So electron has no space to go away from the surface. Only solution is stay away. Atomic scale thickness means electron will confine in those atomic scale thickness only, so you can control it from the gate. And another is find out some material which will have better fundamental properties than silicon, or at least comparable to fundamental properties than silicon, with dangling bond free and atomic scale thickness. Okay. So this people started hunting about that.
So what is the minimum thickness so that in relation to the charge will be
Charge only on the
surface, free motion.
that will depend on how much voltage you are applying from the top.
That's what I'm saying.
There's nothing
If you make it very, very thick.
There's nothing for minimum. So what you have to do, all depends on the how much voltage applying and how much your boundary potential is. If you solve the Schrodinger equation, then how much boundary potential you are applying based on that and which mode you are talking about. Based on that, you carry up wherever you get the peak of your charge depends on that. So standard it will depend on how much your boundary potential is. So there is a concept of minimum. If you even larger also, if you handle the fundamental mode, then you can get it. So it depends on different conditions. Right. So yeah. So what people are doing basically? So people are working in two fields. One side, what we are trying, basically industry is mostly doing this, and of course in some academia also. They are trying to stick on silicon only, and they are trying to evolve different kind of transistor architecture to deal with this technology. Firstly, so if you go and study about the history of transistor, earlier it was planar transistor, then bi-gate transistor came, multi-gate transistor came, FIT-gate transistor came. So these problems mostly they are dealing with to have more gate control, so that since carrier is going away from the surface, so what they are doing, they are wrapping gate around the channel, so that let's say this is your channel, earlier gate was only on the top, so they are controlling channel from the top only, but then by gate came, you have gate this side also, then FIT came, bring gate this side and this side also, so that you can control from all the directions. Then something more advanced gate all around came. With technology means wrap the gate to the channel, so that this control from everywhere. So different kind of, then they strand the channel so that they get the high mobility and all those things. So basically, they are trying consistently improving the transistor architecture to deal with different technologies. And other community, the research community, what they are trying to modify the material, different materials. So two sides. One is industry or some academia, they will find a silicon transistor, but they know that sometimes limit will come. So another side people are talking about different material, they are trying different material which can replace silicon in the future technology. And from this point, something 2D material came into picture. Okay, so why 2D material came into picture? Because three fundamental reasons: dangling bond free, you want dangling bond free, atomic scale thickness, and better property than silicon. At least there can be others also. So, and dangling on 2D material will satisfy all three criteria. So what is 2D material basically? So because see, our 2D material all are in nature exist in the bulk form only. It's not exist in the planar form. They are exist in the bulk form only. But as earlier already have discussed that the 2D material has in plane sigma bond. They are bonded with in plane only. And out of the plane they just have one Raval stack. Like one material on the top, other material on the top of the materials. They all just have one Raval stack. This can be your single layer, this can be your bi-layer, tri-layer also, the bond, but it must have a certain van der Waals stacking over which the material is stacked. Right? So what happens in this case, I think you can easily seal off or you can easily take one material because van der Waals force is very weak. So you can take one material with one layer very easily, which area I have discussed in detail. Fine. All of you are dealing with 2D material in fact. Intentionally or unintentionally. All of you are using pencil, right? It's made of graphite. So if you are writing something, what do you not study? Just a few layers sliding down on your paper, that's it. You are taking pencil and you are scratching it, means it's a layer you are sticking on the page and you are just slicing down, that's it. So you are already removing layer by layer of your graphite once you are writing from the pencil. You know these things? Yes, so basically, all of you are dealing with 2D material. So here only thing is that just deal it more. So it has big family. So I am not discussing detail area, I have already discussed. So it can have monoatomic like graphene, it can have biatomic like phosphorine, thickness. It can try to make like TM reach, or it can have more. My was fine. Last bench. Is it okay? Okay. So welcome on the day 4 of the GAM program. So basically, first 3 days. Good morning, I think all of you have breakfast, right? Yeah. So first 3 days, Professor Ariel talked about material perspective, right? We discussed about different challenges in the material growth and how to get to the material using the exfoliation, using the and different methods of growth. Because whenever you have to deal with any material, for electronics application, first part is to get the material, pure material as much pure as possible. And then after you get the material, then I think one question somebody asked on day 1 or day 2 me. So okay, I have a material in my hand, now what to do? Somebody asked me. So I told them, okay, once I start the lecture, I will start from that point only. You have material in your hand. And then what we have to do next. So just I will give you a bit more again an overview. Ariel give me overview for the material perspective. I will give you overview for the device perspective. And then we'll discuss how to convert a material into the devices and how to do different characterizations and how to get the different kind of data from those things for our application, for the engineering application. So I think all of you must have seen the different material. So one is I think it's a mechanism to integrate this software so that the laser pointer can drag. Have any idea?
So with the screen, what you mean?
No. This is laser pointer. The software also there is something like that.
Okay.
Okay, we'll see. Leave it.
PPT, sir.
Leave it. So basically, if you see any material, any kind of electronic system, and if you break it into top down, I think you guys, some of you must have opened the laptop. Your laptop, right? If you open the laptop, you will see it's made of different ICs, integrated circuits, right? So basically, if you break any system, like a laptop, mobile, or any kind of electronic system, it is made of different kind of integrated circuits, right? If you further break down these integrated circuits, is made of different kind of digital components. Maybe multiplexer, it may be FIFO, it may be small memory element, it may be certain register, counter, or it may be certain comparator or ALU, anything. But ultimately, they are made of certain electronic component, standard electronic component, those are your transistor or resistor or capacitor. Usually, inductor we are not using in the further electronics, because they are current and bulb. So there are standard 3 component, capacitor, kind of resistor, and kind of transistor, right? So these are better. So these electronic components are ultimately made of different devices. If you go further down, it's made of different devices, like standard silicon devices, and it also different kind of architecture, like a standard planar transistor, then bi-gate technology, tri-gate technology, FinFET technology, all those technologies evolve, right? And these all kind of transistors are mainly made of 2 kind of material. Basically 3 usually. Either it can have semiconductor and natural metal, and of course it has dielectric also. So you need certain insulator also. You need certain metal also to interconnect, and you need certain semiconducting material which is required for your particular operation. So ultimately, you see that to make any kind of electronic system, you have to deal with atom to system, and each step you have to do engineering. So from electronic component to system level is the job of circuit designer or system designer. Okay. Here, different type of architecture integration or PDK design and other things. This is a lot of device design, right? And here to explore certain new material. If you want to make certain new material, then this is all of material designer, how to make material and how to get converted into the different, how to enable it for the different devices. Understood? So basically, ultimately you have to get certain transistor. So here, goal of this class is how to get a transistor, and other thing is circuit designer part. So that will not cover those. So basically, we talk about 2D material. But question is, why do we need 2D material? Why do we need 2D material? What's problem? Present silicon technology. If you know the present silicon technology, so basically we are making transistor the silicon technology for conventional electronics. If you have power electronics, then it may be either gallium nitride or it may be your silicon with different kind of doping. So, but ultimately, we want to replace silicon with certain new material. Question is why? So, if you look for the transistor technology, basically, so there are standard things, something known as Moore's law. Okay. So, basically, Moore's law was not actually law. So, basically, long back, Gordon Moore predicted something that chip number of transistors is going to be. I will share all the slides. So it's fine. Nobody. I'll share the slide. So basically, Gordon Moore told that whenever you are making any chip and so you are compacting the transistor, with time the compact density of transistor will be increasing. Basically, it will get double in every 18 months to 2 years. Some initially it will 2 years, then again it will modify for 18 months. Right? So compact density of transistor will be double. Why? Because it will give you different kind of advantage. It can give you power dissipation advantage, and majorly cost and speed advantage. So basically, Gordon Moore predicted these things. And if you see the evaluation happen in the transistor architecture, when I'm talking about transistor architecture, I'm talking about this level. Whenever I am talking about transistor architecture, I talk about this level, different kind of architecture. Okay. So what kind of different transistor architecture do we? So basically, if you see this was the first transistor. Picture, if you see, if you go in Google and you can search about the first transistor, this was the first transistor. Then again, first planar transistor came into picture. Then basically your high dielectric came into picture, and this is the most advanced technology which are using in these days known as different technology. So these are the basically device architecture of transistor. Once you change the device architecture, corresponding you see that the chip number of transistor also increased. Initially your single transistor chip, then 16 transistor, 45 transistor, and this is latest basically silicon or bionic transistor, basically in the billions of transistor in a single chip. So consistently your transistor technology evolved, consistently your chip technology evolved. Right? Once the consistently chip technology evolved, you can see that your gadgets also evolve consistently. Right? So you can think that how engineering at device level modify your final engineering at the gadget level. Right? So if you see the first computer, this kind of your early days, India's first computer kind of thing, and then computer consistently evolved, and then now we are looking for something like a smart, flexible, complete system. So consistently engineering is driven at transistor level also, and this is driving different kind of thing. But question will be, if we consistently drive transistor level, till what point? Because in whatever our goal is, we are shrinking down the channel of the transistor. But of course, we shrink down not only the channel, basically we are shrinking down to the different side. We are thinning down the gate or the body also and everything. Scaling means scaling from different side. So if you do this, then there will be certain limit, of course. And what kind of limit it will be? So if you go and explore this, then scaling used to happen with something like a standard Dennard scaling law. So what Dennard scaling law suggests that you don't go in digging deep. So just he suggested that you modify all the parameter of transistor certain factor K. That's it. The main idea is to you shrink down the channel length, whatever he suggested. But if you shrink down the transistor consistently, I think Ariel also discussed about this. There are so many effects evolved from the 2001 watts. Those are known as short channel effect. There are different kind of effect came, so I will discuss in detail. You can explore. That can be our source to drain tunneling, that can be gate tunneling, that can be band to band tunneling, and that can be your quantum confinement and other stuff also. So different kind of problem starts arising. And once the different kind of problem starts arising, people are trying to address different methodology to handle those kind of effect, and people are trying to consistently enhance our technology or consistently better our technology. So if you see that different kind of evolution happen, like sensitization technology came, then people use high-k dielectric, people use ultra-thin film, then people use multi-gate. It has big family and it has wide range of properties. It provides you a wide range of mobility also and provides you a wide range of band gap also. So means wide range of mobility means you can get better and better electronics application in terms of the speed, and wide range of band gap means it can provide you different kind of optical properties so that you can get different kind of optical detector and other stuff also. So from the family, of course there are plenty. I think if you go and explore, there's more than more than 700 or something people have already explored. And since after the implementation of the ML and AI computational technology, people are predicting huge. People have predicted a lot of coding to 30 million. But a standard, if you talk about, there are 4 materials which are leading in the race now. So those are basically graphene, phosphorine, TMD, and HB. So what are these? If you talk about graphene, it is made of carbon, in-plane carbon single bond, which already Ariel discussed. Phosphorine, Ariel also discussed about this. What is this? This is basically biatomic 2D material. TMD, that also Ariel have discussed, which is MOS2, MOSE2, WS2, WSE2, many others are also, which is basically triatomic 2D material. Fine. And then you have HBN here. So HBN has similar in-planar structure of graphene, okay, but it's made of boron and nitrogen in-plane form. Instead of carbon, it's made of boron and nitrogen. But even these 4 2D material itself will give you a wide range of application or wide range of properties. So some of I have highlighted here, so you can get it some of the properties. Interesting thing is graphene and 0 band gap. Lot of carrier, but which we can control to the gate. Phosphorine, beautiful material, especially its property about band gap will be direct with the number of layers. That's a very, very interesting property and interesting application. TMD has the significant range of band gap and mobility. And HBN is a wide band gap material, so you can use this as a 2D insulator. So on application point of view, because if you make any transistor, you need metal also, you need semiconducting material also, you need insulator also. I discussed in the first slide. So to bring a complete 2D technology, you need 2D semiconductor also, 2D insulator also. Then only you can bring the complete 2D technology at device level, right? 2D material, metal if you will not get that, you can deal with normal metal, no problem. At least you need 2D channel and 2D dielectric. So basically, HBN is very interesting and find 2D application concern and the wide band gap optical wide band gap optical application like UV or something. So basically, one by one, if you see, graphene, a very interesting fundamental property is a 0 band gap. It has single atomic monatomic structure, and it has very nice phonon band structure also. One more people have discussed, somebody asked me 2-3 days ago, I think second day or first day of the program, that some material does not have carrier, then how it can be a very good thermal conductor. So let me tell you clearly, electrical conductivity and thermal conductivity are 2 different things. Once you talk about electrical conductivity, any material can be electrical conductor only if it has free charge carrier to move. Once you talk about the current in any material, basically current is basically rate of flow of charge, how fast your charge is flowing in your material. That can be electron, that can be hole, that can be any ion, or that can be anything. If you have free charge carrier in any way, then that material can be a good conductor. I'm not saying must be, that can be a good conductor, no problem. But fundamental things required for to make any material a good conductor, you have to have a free charge carrier inside a material which can move once you apply electric field across the material. So this is the fundamental requirement of electrical conductivity. Thermal conductivity means if you talk about thermal temperature, so let's say if you talk about any kind of material, let's say it's any kind of material. So mainly whenever you are talking about thermal conductivity, Temperature means basically vibration of all the material. If you have basically, if you are not dealing with 0 Kelvin at higher temperature, these all bonds used to vibrate at any temperature. So basically, if you go and explore about fundamentals of temperature, it's basically linked with the vibrations, which are known as phonemes. So once you talk about thermal conductivity, means how this vibration can move from one part of the material to other part of the material. Now this vibration can move in two ways. Either your electrical conductive carrier can take certain energy, can collide with this phonon, can take certain energy, and can go to some other place and again transfer the energy. Or these vibrations, this can collide with this can collide with this can collide with this can collide with this. So through phonon collision only it can propagate. So electrically, only one way, only carrier can move from one place to other place. Thermally, to make the thermal conductivity, to transfer thermal energy from one point to other point, it can transfer through phonon or phonon vibration or crystal oscillations also, and it can transfer to the free carrier also. Both way it can transfer. Right? So that's why in early days, basically, what people need to understand that okay, no, only metals. So that's why if you talk about metal, so metal major contender to transfer the carrier from one point to other points are free carrier because they can move fast. Okay, so free carrier. And so if you deal again specific heat of depend of due to the carrier due to the phone and the vibrations that you can deal with, but some other material who does not have free carrier also they can be very good thermal conductor. It all depends on how fast this phone, this vibration will propagate from one point to other point. Right? And that we can explore by something known as this phone band structure, which I have calculated even for graphene. You can calculate phone band structure for other materials also, which in quantum mechanics sessions tomorrow you have, or today only, not today you have that, you can ask them, they will. So basically, formal band structure. And so whenever you talk about band structure, you need both electronic band structure and formal band structure also. Basically, you can know the dispersion, and then only you can explore the actual fundamental property of the material: electronic, formal, thermal, electrical. Right. So the beauty of the graphene is graphene has very high thermal conductivity also. Right. So it's has very high thermal conductivity. Usually people talk about graphene has zero band gap. What's interesting, graphene has zero band gap in or zero energy gap in electrical band structure also and thermal band structure also. Electrical band structure you can see there is no gap between valence band and conduction band. But thermally if you explore about that thermal kind of phonon, the material has two kind of phonon. One is known as optical phonon, one is known as acoustic phonon. So optical phonon means at some point you have heat getting trapped somewhere in a standing wave. And acoustic phonon means it's traveling wave. So whatever heat is getting generated at some particular point, it can travel. So if there is no, so these all are optical phonons. So there is no gap between acoustic phonon and optical phonon, then comparatively they can give take heat very fast from the optical energy to the acoustic phonon. So graphene does not have energy gap in between optical phonon and acoustic phonon. Right? So this is another very interesting property for the graphene. So what you can do, so whenever you generate heat at any point in the graphene, its corresponding acoustic phonon also has the similar energy. So it can transfer quickly from the particular point, and then the thermal conductivity of graphene is very high, it can easily travel from one point to another point. So that's why graphene can be very used, strongly used as a heat spreader also. A lot of people in these days are exploring graphene so that it can be a very fast heat spreader, especially in the electronic chip. It can take heat at one point and spread across different places. So it's a different domain of the investigation. Major problem with the graphene is the zero band gap. It does not have band gap, so logic application is very difficult to use. So one burning problem in the research, people are trying to make zero open the band gap in the graphene. Right? Phosphorine. Once you talk about phosphorine, it's a beautiful material, especially I like this material a lot. It's a property and I like this material more than the graphene. Especially it's a tunable band gap. Layer by layer. it has many standard issue, many different property. One big problem is its ambient unstable. If you leave phosphorine, it will degrade automatically. So if you deal with the phosphorine, you have to make it insulating, encapsulating properly in some way, so that you can deal with the material. Since it is ambient unstable and due to different kind of reactivity property, still people are struggling to grow this material. Until unless you will not grow using some material, you will not synthesize properly, it will not be scalable, then you cannot use it in the technology level. Right? So these are two challenges, the phosphorine. And then TM leach. This is also a good material. It has different kind of property, but here the problem is it has a lesser mobility than the graphene, even it has a less mobility than the silicon also. Right? So it has mobility a bit less. And another thing is with all the materials is contact resistance. What is contact resistance? So let me discuss a bit. What is resistance?
Sir, answering similar
Graphene?
like graphene. Answering other similar.
No, byproduct.
So what are the
No. A single atomic element, yes, it's a phosphorus only. Yeah, phosphorus.
so like black black phosphorus.
Black phosphorus. Black phosphorus. Single layer of black phosphorus. Single atomic? You are saying single atomic layer or single atomic element? Which you are saying? Element, single atomic is made of only phosphorus. Right? Black phosphorus is a material, ultimately it's atomic, made of phosphorus. Right? So basically, what is resistance?
Contact resistant source.
The normal resistance.
To oppose the flow of current.
Something which can obstruct the flow of the current. So basically, if you talk about any silicon transistor architecture, basically you see just a standard silicon transistor architecture I'm giving you is something like this. It has N plus, anyone can be source, anyone can be drain, this is insulator, this is metal or poly, this can be gate. So in any silicon transistor, once the current flow, let's say for example, you supply here, the electron will flow from this point till metal channel, and it's good to go like this, right? So if I'm saying this, strictly not this lines, this pass this way also. Don't think there's no way to flow on straight line. Don't think about that. So basically, it can hatch obstacles at each point. Whenever you deal with a material, there's a standard scattering inside the material also. And a lot of scattering used to happen or resistance used to happen at the interface. Whenever you are dealing with those two different materials, the interface have completely different property than the bulk material. Right? So here, metal to this material is one interface here, and then standard resistance in the channel. Standard resistance in channel, all of you know, electron can strike with the phonon, and due to that resistance is to out. But on interfaces, two materials are combining at the interface. Just think about these two materials are combining the interface. This has dangling, this has different property. No, there can be lattice mismatch, there can be different kind of properties are there. So whatever resistance due to different properties of the material at the contact, it's resistance due to interface resistance of the metal and any particular material are known as the contact resistance of the carrier. So silicon, we don't have contact resistance because we have different kind of technology, silicization technology, where we already have dealt with the resistance, no problem. Another thing is that silicon, which we are talking about, is channel resistance is significant. Contact resistance is very less than the channel resistance, so it is not very important for the silicon. Because we We have high deep doping technologies and different discussions, so you can see. But if you talk about 2D material, 2D material have different standards. So 2D material has contact, all the 2D material very high contact distance. If you check about any standard interface, let's say if you are making any standard interface, one side you can put metal, one side semiconductor. So basically there are different kind of barriers are here in terms of the potential which you can explore in the device. This is basically one is whether your metal is coming very close to your material or not. If you talk about the silicon or bulk material, all material has the damping bonds surface, right? So if metal approach this material, what will happen? This damping bond can get easily overlap with metal's damping bond. So interface bond will be relatively strong in the bulk material with the metal. But if you talk about the 2D material does not have any damping bond in this direction. Right? So bonding, if you put metal on top of any kind of 2D material, the bonding between the metal and the 2D material will be weak as compared to any other bulk material because it does not have any damping bond in this direction with 2D material. Metal has, but 2D material does not have. Right? So what will happen? There will be a standard gap between metal and the material at the interface, which is something known as your tunnel barrier at the interface. Because carrier has to cross it. If you find out its potential profile, then there will be tunnel barrier at the interface. Right? And then apart from the tunnel barrier, with the standard interface potential structure, which is known as the Schottky barrier or not, that you can explore by the book. So what is basically Schottky barriers? So what you have to see, if any standard structure, one side you have metal, one side you have semiconductor. Right? So what will happen if you go and deal with any metal? So first you find out the Fermi level. Fermi level is something level you have to understand up to which your electron is filled actually at 0 Kelvin. Fine. But a standard temperature also you can think about that, okay, for the better understanding. So Fermi level you reach up to some level which you have significant amount of electronic states which are filled basically. So if some material has to jump from the metal to semiconductor to flow, material has the carrier has or electron has to come from this Fermi energy state to the conduction band of the semiconductor. It has to go in conduction band. Valence band is completely free. If you are talking about electron turn, it will not flow in the valence band. So it has to go in the conduction band. So it means that let's say that it is vacuum level something, and you have to align your energy of the electron properly to flow from this to this. Let's say that if electron will means Fermi energy, let's say I am here and I will go down, then I can go easily, right? I can walk on the stairs, go down easily. I don't need any kind of energy. I can go easily. So if your Fermi level is here, conduction band energy is lower than the Fermi energy, then electron can go easily without any kind of barrier. It does not need to put any effort. But if I have to go up, then I have to climb. I need certain energy so that I should climb. Similarly, here, if conduction band energy level is here, then electron needs additional energy to go from the Fermi state to the conduction band. So this is known as standard barrier at the metal semiconductor interface, known as Schottky barrier. Right? So for dealing with contact, you have to deal with the Schottky barrier. Also, if there is a Schottky barrier or not, you have to deal with tunnel barrier also. Especially for the 2D material, you have to deal with Schottky barrier also, you have to deal with tunnel barrier also. So Schottky barrier, if you deal with, what you have to do? Schottky barrier cannot have in your control because all material have different Fermi energy state which you can know by their work function. So you can pick some particular semiconducting metal whose work function should easily align with conduction band of your 2D material. So that's why if you pick any kind of 2D material, favorable contact metal is different for different 2D material. Because the first requirement is you have to align for what function of the particular metal to your 2D material so that you can minimize Schottky barrier or Schottky barrier height, you can minimize the Schottky barrier as much as possible. This is the first fundamental things. Understood? Second thing is, if you choose any particular material, then you want to minimize this interface tunnel value. So these two are the primary challenges if you discuss in 2D material or device perspective. If you take any 2D material, first standard question people will ask you how much contact resistance of your device is. Because contact resistance is a very big challenge for the 2D materials. A lot of people are doing research to reduce the contact resistance of different 2D material, and they are trying to find out proper metal so that you can minimize the contact resistance as much as possible. Right? Question to this point?
So you have talked about the insulator, but to make the complete 2D device, we need a 2D insulator.
Complete 2D material technology, that I do.
Yes, sir.
But what you can make 2D, 3D other insulator also, no problem.
So what may be the 2D insulator?
2D?
Insulator. What we should choose the 2D insulator?
HDI. There only one standard amount of 2D material is HDI.
So we replace the contact with also 2D material.
Contact?
Also 2D material.
Contact means you are talking about metal. Completely you cannot replace because ultimately what you have to do, you can put, but you have to ultimately you have to integrate your device with external world. Your external world is 3D. Ultimately, anything you have to connect properly with external light, right? Which you cannot handle micrometer range or millimeter range. That's at least in millimeter range. Ultimately, if you replace internal bus with 2D, ultimately somewhere 2D to 3D integration you have to do.
So, but there is a very existing graphene contacts.
Existing?
Graphene based contacts.
It's fine. So let's say this is your graphene device. You put graphene as contact. You take this metal out. But once you connect internally with external world, somewhere you connect with your external metal, right? External element, right? Then the contact problem will be here. Ultimately, that interface will come at some point. You can internally you can say, okay, graphene contact, fine, it's fine. But ultimately, if you are connecting pen type, you are connecting certain wire, right? So ultimately, somewhere you have to connect the 2D device with our 3D, our world with 3D. So somewhere 2D to 3D integration will happen somewhere. Right? So somewhere this interface problem will come. 2D to 3D interface problem will come. Any other question?
Channel variable. How to do this?
I'll discuss about the whole PhD on that. Okay. So I'll discuss about that. So basically, I'm telling you since you asked question here, make tunnel barrier due to this bonding, right? Lack of bonding. Metal has the bond. Somehow you create the dangling in the graphene or in the material, and that dangling will create bacteria with certain defect. Right. So you remove certain carbon atom, you create certain defect, certain overlap of orbital will be there, which is not saturated. They can bond. So we have done it computationally, experimentally, everything is verified.
You fix my carbon.
Not a strand. We know to a strand what we do. Basically, you bombard some ion to knock off some atom.
Not to create defect, but lack of influence will be there to control that.
You want contact metal and here contact lattice mismatch will not be problem because if you deposit metal is amorphous, not crystallized. So putting metal, depositing metal is a crystallized amorphous structure. So amorphous structure is settled down, settled on a particle. Right?
So, creating dangling. So you remove the atoms. So how? What are the other materials?
I'll discuss about it. I will not discuss about device flow. How you like that. Okay. We are not putting anything there. Any other question? Yeah, so basically, if you list down challenges in different 2D material, these are the primary challenges. Right? You see that graphene, zero band gap, high contact resistance, deal with both things. These are fundamental primary challenges. After that, other more challenges will be there. Growth perspective, Ariel have discussed, there are a lot of challenges in the growth. I am talking about device perspective. Device perspective, graphene, open band gap somehow and reduce the contact resistance. Phosphine, find out the root cause of the stability, and then it has also a high contact resistance, encapsulate the material. TMD, of course, it has high contact resistance. Right? So, these are the primary challenges which you have to deal with and address with. Once you deal with these primary challenges, address with these challenges, then you can enable your 2D material for the technology level. You can enable at primary level, not at final level. Because I'm talking about material, then problem will come on the device level, problem may come on the circuit level and system level, this is a different story. So it's a long journey. Okay. So basically these things are there. So with how to deal with primary challenges, how to address those primary challenges. So for that you have to do consistent research and engineering on the material. So how to do it? So Eric, one thing.
So you can easily open the band gap in the graphene.
So you can easily open band gap in the graphene.
How we can open the band gap in the graphene by applying external voltage or by chemical coating, right?
No, it's not easy. Don't say it's easy. In applying external voltage, you cannot open band gap easily. How much voltage you can get with the open like this?
You have to drastically decrease the mobility.
Have you tried? Yes, you can open a bit, especially the bi-layer graphene, not in the monolayer graphene. Monolayer graphene opening band gap very, very difficult. Theoretically, DFT will tell you that you can, but it will degrade your other graphene property. Opening band gap in graphene is easy, but I don't achieve yet. Graphene came in 50 to 50% form. Still people are trying to achieve it. Okay. Chemically also, it's not easy to open the band gap in the graphene. But some people may claim you that put oxygen plasma and get the band gap. Actually, it's not graphene. It's graphene, basically graphitic oxide. They are converting graphene to graphitic oxide. It's a different material. It's not graphene. When you convert different material, you can make a diamond. You use band gap. Persisting property of the graphene and then of band gap, nobody has achieved yet, as far as I know.
So how can we reduce the contact resistance?
We'll discuss it. That's right. So basically, the question is, if you have to deal with primary property, then how to do it? So first thing is, you should have material in your hand. That material hedge, Ariel had told you. Then now you have to convert those material into the FET structure. Once you convert into the FET structure, field effect transistor, then only you can find out how much mobility is, how much is contact resistance is, how much other property is. Fine. So you have to convert, so you have to learn how to convert material into a FET structure. Clear? So if you talk about standard silicon transistor, once again, so what is our goal here? You have to make a standard FET structure. Standard FET structure means you need certain material. Then you need two contact for source and drain, right? Two contact, one can be metal contact for source, drain. This 2D material will be a certain substrate. This is your substrate. On this substrate you have 2D material. And then you need gate. Gate means With 2D material, you need certain insulator, then metal. Means on 2D material you put certain insulator, then you put metal. Fine. And then metal. This will be your gate. So you need source, drain, and gate to make any kind of flat structure. Source drain is normal metal contact with the material. So you have material, put metal at 2 point, that can be your source and drain. For gate, first you put certain insulator on the 2D material, and then you put metal. So usually, what if you are putting 2D material here, usually most of the substrate you are using, those substrates are insulator only. Whatever substrate you use, that's it, insulator only. So what we are investigating 2D material two way. One is known as top gated device, one is known as back gated device. Top gated device means you have material, deposit certain insulator first, and then deposit metal. This can be your gate, right? So this is your top gated device. Back gated device is very easy because you already had insulator below 2D material. Your substrate is insulator. Your substrate is insulator means you already have insulator below the 2D material. Just somehow you make this surface conducting and you can put gate here. Fine. So remove this part. This is material. This is already has insulator. Somehow put this bottom conducting and you can get the backdated. In bottom conducting you can get it easily, just put surface or substrate on some metal, that's it. Whatever substrate you have, put on certain metal, that's very easy. Fine.
Top gated whatever dielectric or insulator which you're using, the thickness will be the nanometer, right? But water treat, water substrate you're using is in micrometer.
Very good question, sir. I'm telling you that. Very good question. Okay. So basically, he told that, ask that if you put any gate, then the gate has to be not nanometer necessary, micrometer also you can do, but few nanometer, 100, 200, 300 nanometer. But whatever is, so he told that if you put any substrate, the substrate can be in the range of micrometer or higher also. So how to deal with it? So usually there are two methods. Usually when you are using a standard substrate, you are using silicon dioxide, silicon. You are using doped silicon. So if you have silicon substrate and if you dope it, it has free carrier there. And then you put silicon, then oxide on the top, probably I think 90 nanometer oxide on the top. So your substrate is silicon dioxide. So here to here these are conducting. Only just top on the silicon, you have around 90 nanometer or 180 nanometer, your silicon dioxide is there. And then you put your 2D material here on this top. So your substrate width is actually this, but your here to here is highly doped, P-type or N-type wafer. So if you buy a silicon wafer, it will ask you whether you want P-type or N-type wafer. Means till this point to this point, this is conducting. Only insulating part is here, which is silicon dioxide. Fine. That in the range of nanometer. Okay. Clear? Another thing is, if you go for top gated device, you have to deal with the less gate voltage in the order of volt, 1 volt, 5 volt. But if you go for a back gated device, so if you increase your width, then correspondingly you will scale your voltage. Let's say 5 times you increase the width, you increase 5 times your gate voltage, and things will be done, no problem. So if you are using top gated device, you have to deal with 1 to 5 volt gate voltage. If you go for the back gated device, you go for 30 volt, 60 volt gate voltage.
Source and drain are also far.
Using the source and drain are the
Source and drain are in top gates.
so ultimately, you need some gate contact to control the channel conductivity. That's it. Fine. So initial research level, back gated device will give a lot of advantage in making device. I'll discuss that. Making back gated device is very easy as compared to making a top gated device. So if you initial level 2D material research, I suggest people use to make just back gated device. It's very easy. I'll discuss the process flow. You can make it very easy, but To go for top weighted device, you need triple layer or double layer masking, and you need a lot of lithography. So I'll discuss the process flow how to make device. Okay. Any other question here? So we have already discussed different synthesis method of the 2D material, so that already you have. Now we have to convert your material into the device. So what's our primary goal? Let's say you have 2D material. First we'll discuss how to make the backdated device. How backdated device will look like? I am talking about, I will make backdated device with the silicon. Silicon substrate. So you need certain structure. This will be silicon. This will be SiO2. Then you will have 2D material on the top. And then you need certain contact at two places. Source, drain. You need this kind of architecture, right? Your gate will be your backdated, right? So basically, and how will you get to 2D material? If you don't have any synthesis things, so then you can go for exfoliation. And exfoliation, all of you have seen in the lab, right? How we do. We take a scotch tape and then you can put in the substrate. So he has did not show you that before exfoliation you have to do a lot of cleaning. Because you are dealing in the range of nanometer, micrometer. And how much your hair size? How much? Hair thickness is micrometer. No, it's millimeter. 400 millimeter or something. Okay. So you can think that if you doing the processing and when you work, one hair will fall on your sample, it will cover everything. You can go and explore on the internet. So your transistor size is lesser than your blood plasma size also. So you can think that how clean process and how clean environment and they will required to deal to make all the transistor processing. So that's why most of the things which we are doing is in a standard clean room. So we explore about the clean room, or if you need other discussion, then we can have separate session on that, or how the clean room works. So main takeaway is whenever you are processing, while you make any device up to transistor technology, every step has to be very, very clean. Right. So all process start with substrate cleaning and then material synthesis. Here synthesis means exfoliation. Right? So you substrate, you clean, and then you transfer your 2D material or your SiSi2 substrate. SiSi2 substrate you can easily get into the market. If you want to know how to get it, then go and study about the silicon wafer fabrication method. You can explore about that, it's a separate course. But easily in the market around in 2500 you can get a full wafer. Oxide oxidized full wafer 2500, 300, 2500 or 3000 you can get into the market, and that you can dice it and you will convert it to the die. Right? And then you can take the scotch tape, you can take silicon SiSiO2, you can just exfoliate it. And after exfoliation, you can see to the microscope, and based on the contrast, based on the Raman, you can find out mono or pure material. So till this point, all of you understood, right? So till this point, what step you have in the end? Silicon, then SiO2, and then 2D material. So up to this step, I think you don't have any problem, right? This is p-type or n-type, this can be conducting. So conducting insulator and the 2D material. This step we have. So in the back gateway, just you have to worry about to create two contact pattern. That's it. Because you already have gate. Gate you have already prepared here. Just you have to create two contact for source and drain, and your whole FET structure will be ready. Now how to go with that? To put any metal, you have to deposit metal. So there are standard method, thermal evaporation, EV evaporation, sputtering, all those things. Deposit metal. But here is, let's say, whenever you deposit anything, any system deposit anything. Deposition means you are converting metal from a standard solid phase to certain vapor phase, either with thermal evaporation or through a sputtering or through EV evaporation. So if you put, let's say, this is SiSiO2, you put it, you evaporate metal. So metal will go and deposit everywhere. But you have to put only a two spot. So if you expose directly for the metal deposition, it will evaporate and it will get deposited everywhere. So first part you have to do metal deposition before part you have to do something like masking. Fine. And to mask it properly or to transfer pattern something standard in the you have to go for lithography. Fine. So you need lithography to make source and drain contact. Fine. Now how to make the lithography? How to go for lithography? So basically, whenever there are two standard methods of lithography, one is known as optical lithography, one is beam lithography. So main element of lithography are two standard process, three standard process basically. First, we need some material which are known as resist. So what is the resist material is basically resist is certain or usually it's organic material, certain organic material whose property you can change by certain exposure. If its property will change by light exposure, it is known as photoresist. If its property you can change by beam exposure, it can be beam resist. Right? In all kind of lithography, you need certain material whose property you can change by exposing something. That can be a resist. In photolithography, what people are doing, people are changing. You are using a standard photoresist in which if light falls on the certain area of the resist, its property will change. Property change can be anything, it's fine, but its property will change. Similarly, if you are doing EV lithography means if electron beam will fall on certain area of the resist, its property will change. Okay, understood? So let's talk about EV lithography. Then a standard resist of EV lithography are something known as PMM. Fine, so organic material. Basically, why you use EV lithography? To understand that, you have to understand what is the difference between optical source and beam source. So since you are doing exfoliation, in exfoliation you cannot predict when the flake falls on the wafer. It can fall any time. So you need highly controlled exposure, means you want to expose in certain particular range. So that better control you have in EV. So EV you can go for electron is very small and you deal with high energy, so it can give you very small features. So that you can study separately. So basically, if you have EV lithography, so what we are doing basically, let's say, if you have a standard SiO2, what I'll do, I'll coat PMMA on this. On the 2D material, this is on that I'll first coat PMMA. How I'll coat the PMMA, you take PMMA, you have a SiO2, I'll do something drop casting, I'll drop couple of PMMA on the surface, and I'll do a spin coating. A spin coating means you mount those things on your something which rotate very fast. You mount it, so what will happen? It will rotate very fast. So whatever drop cast you have, that will disperse everywhere on the surface. Understood? All of you? So we have a SiO2, let's say this is. Let's say this is a SiO2, 2D material and PMMA. Manganese are 4 colors, fine. Silicon, SiO2, 2D material, this is PMMA. So how do we duplicate it? So on SiO2, we put some drop and then we rotated it very fast on the machine, so it dispersed everywhere. So now we have PMMA everywhere. So let's say this is you have PMMA. And then what we did, and what we will do, basically you expose E-beam in certain area. E-beam gun at in the range of nanometer spot size. So you can control E-beam gun so that you want to expose E-beam only in these two range, only here and here. I will not expose everywhere. I'll expose E-beam only in these two range, here and here. Which is the standard? If you are using optical lithography, expose light here and here with help of mask or something, or if you have resonator, you can put that. So we will expose this light or E-beam depending on whether we are using optical lithography or optical lithography here and here. Clear? So what will happen? Property of material will change here also, and property of material will change here also. So this method is known as exposure in a standard lithography system. Right? Then what we will do, since now this material PMMA are here to here, but property in this area and property in this area are different. Its internal atomic orientation and other things will change. So what will happen now? We have certain chemical, that also is a standard organic chemical, associated with this resist. So what that chemical property is, that will have different chemical reaction with this area and this area, because these material are different now and these material are different. If you put that in certain chemical, that will react from this area, that chemical either can react with this area or it can react with this area. It depends on whether you are doing positive lithography or negative lithography. Leave it about that. A standard, what you understand now, that if you dip this whole thing in certain chemical, it will react with this area and this area will get removed. Right? This is known as something known as developing in the lithography system. After exposure, what you will do? Developing. So you dip this in certain chemical. Since property of this area are different, those chemical will remove this area also and this area also. So what structure you will have now? After developing? See? Your next structure will be something like this. Something like this, right? On PMMA. You have gap here. Right? Is this point understood? After developing? Now exposure in developing, basically optical lithography have different developer. If you go for EB, which has standard MIBK developer something, right? Now what you will do? Now you deposit metal. So what you take this system, mount on the certain substrate on the top, and you deposit metal on that. So once you deposit metal, the metal will come here. Where? Metal will come everywhere. Here also it will come. Here also will come. Everywhere metal will come, right? Because you had took it, evaporate metal everywhere, so metal will come everywhere. Fine. So if you see now, here is the catch, and this is the main thing which you have to do something on optimization. See, if this thickness is a small, very small, then this metal and this metal can be connected. So everywhere metal will be connected. So you have to keep this thickness enough large, so that there should not be connection between this metal and this metal. Fine. You are getting or not? Because you have put it and metal is getting deposited. If you deposit for more time, then again this trench will get filled and this can get connected with this. So there should be a proper trade-off between your resist thickness and deposition time. And deposition time you cannot compromise much, because you need certain thickness metal here also. You need, because your contact has certain thickness also that you want. So if you want this certain thickness here, then you have to deposit with certain time. But that should avoid to get overlap with this. So this resist thickness has to be significantly larger than the thickness whatever you want here. And that you can achieve by proper spin coating. So if you do first time all these things, then you have to do this multiple times, spin coating till deposition, spin coating till deposition, spin coating till deposition. Right? So after this, what will happen? Standard thing that standard you have metal. You have metal here, and you have metal here. Everywhere you have metal, right? And then what you do, you dip this whole system into some another solution, not the previous solution. Previous solution reacted only those area in which you have exposed, resist is exposed. Now you dip this in some other solution which can easily react with resist, all resist. For PMA, the standard solution is acetone. It's organic. You put in acetone, it will easily react and remove the organic. So put into the acetone. So what will happen here? The moment you put in the acetone, what will happen? Acetone start reacting with these, because there is gap here, right? There is a gap between here. The acetone can easily enter through this area and it will react with all the PMMA. Now, if moment PMMA will react with this PMMA will get removed, this metal will also get removed, right? If PMMA will remove this will also get removed. If PMMA will remove this will also get removed. So finally, what we will get? This is SiSiO2, and then you will get two metal contacts. Understood? If this will not optimize, if there will be connection between here and here, then your whole metal will go away. So there are a lot of failure used to happen on this process known as lift off. This is known as lift off. So there are a lot of failure happen in the lift off, because if you have not spin coating properly, or if you have not optimized your deposition time properly, if there will be any connection between here and here, or here and here, or here and here, your whole metal will go. Fine. So that's why if you go for any kind of process flow, it must not be random. It's completely crystal clear protocols are there. How much should be your spin coating time, how much should be your baking time, how much should be your deposition time, how much should be pressure, how much should be temperature, everything has to be precise. If you deviate a single parameter at any point of time, it can be a failure with the laptop, you may get into the failure structure. If it will get successful, then you have a standard backdated fetch here, where you can, this will be your source, this will be your drain, this is your oxide, and this will be your, you can connect, you put on metal, this will be your gate, but in fact the gate is to this point because these are all connected. Fine. Question. This is this till this point is not your conducting line. Now you put any metal thing, you put this on the surface, there will be contact here.
But if your downside is unpolished, right?
Wafer downside is
Unpolished or completely silicon.
so for that, so that's why if you downside unpolished, then what will happen? There will be certain insulator. That's it. But ultimately you are putting voltage, so get control to give you. There will be certain, it's a very good question. So he's saying that if you are taking wafer, its downside is polished. Yes. So whenever you go for any kind of oxidation you prevent both sides. It will prevent top side also, it will prevent bottom side also. So it will reduce your effect, it will increase your effective gate oxide width. So ultimately, if you are taking it this is 90 nanometer, then ultimately your one oxide is here, one oxide here. So it can be 180 nanometer. It will not affect your gate control. If you apply the voltage, gate control is what? You change the voltage here and you want some effect here. So that field effect will come here, it will not give you problem.
Limitation of backgated, sir.
Huh?
Limitation of backgated.
Limitation
Compared with the top gate.
It's on technology level.
Yes, sir.
See, first thing, if you are going for research perspective, backgated device will give you easily. Now see the complication of top gated. Top gated, what you have to start first, you have to deposit dielectric here. So before metal deposition, we need certain architecture, right? So if you have silicon dioxide, you have 2D material, first you have to put dielectric here. Whatever insulator you want, you have to deposit first insulator, and then you can go for ALD or you can go for something.
Limitation of backgated. Top gated, I got.
So backgated you cannot use in the technology. Vaporous you can use because whole vapor will have common gate here. Ultimately, in the transistor you make, then you need independent gate for all the transistor. But here, what happened? I have a size I go to. I have different flakes are there. I can make different devices. So my gate is same for everybody because gate is controlled. Complete vapor is controlled. So common gate for all the transistor is good. For exploding purpose it's fine, but for technology purpose it will not be very effective. Okay.
High bias will be needed.
High bias will also be needed because this gate is away from the channel. You need high bias point also. So this is very useful for study purpose, technology development. Let's say if you are dealing with contact systems, you need better structure, you can get the better structure. If you are studying the channel property, you can get it. And most importantly, for the sensing purpose. Because sensors, you want to expose the sensor. If you put gate from the top, your sensor, your surface will not be exposed. So there you need in fact backgated device. So that channel should be open, so that if some gas will can come and can interact with the channel. So for sensing purposes, you need this kind of device. So your channel should be open so that it can get react with some gas or something. Okay. For sensing purpose, this will be very useful.
But in the latest indicated circuit technology for sensing application, they are using the top gate seams.
They are using top gate because they have some different kind of technology where the gas can go. So that have different kind of technology. They are not using backgated much, but today will use the backgated. So what's your question?
I'm saying they are using top gate.
They
It is sensing also.
they're using the top gate.
It's including thickness by any
Explode in situ.
monitor how much thickness they are doing.
In situ means it's a spin coating and real time thickness.
No, even after the
That you can do measure using a electrometer. You can go and measure that. You do a spin coating and you have electrometry, you can go and measure. Right. So best way is just do electrometry. There is one depth tech also. Right. So best way is to do or any other kind of optical characterization. In situ means you integrate your spin coater with the that instrument. In situ means integrate your fabrication and characterization both together. That's it. In situ together.
this silicon oxide, the same configuration. Let's say before doing anything, part of silicon oxide I etch it out. I have a silicon oxide as well as silicon iron.
You are saying that you have this down silicon oxide.
So that if I make some contact, that's the back take there. Then we take issues.
Back you are saying that this will remove, right? This one.
Instead of placing the rack, not it there, I just remove part of SAO2 on top of it. That I can make a
That will give you a complete lot of process challenge. First you have to do etching SIO2. And etching, if you want to do first you have to do lithography, then etching. Because etching again you do with ion etching, some bombardment will do. It will expose everywhere. First etching also you have to do first lithography. So that you mask other area and you expose only the area where you want to etch. So first lithography, etching, and again you have to remove resist. So and then you deposit again metal.
Like if I do so, then I can achieve the same thing as below as
Yes. If you do so, you can achieve. The process you can handle, then the device architecture level.
in the same as 1.5 voltage generation.
Yes. But why you bet? You can get on one that on top. Why would you bet? Go to top with it. No need to access etching. Deposit direct insulator and the etching and deposit metal. Any other question? Snacks is here. First. Check it, and then we'll take a short break, and then we'll go for next session. Okay. So now, material to device you have in your hand, right? You have device in your hand. Okay. Now we have to do characterization. First of all, how to different device work, and then you have to go with the characterization. A spin coater, Harsh will show you tomorrow. Tomorrow, today's second half only. Today's second half you can walk. Harsh will show you. Or we'll go tomorrow only. Tomorrow we'll play electrical translation. We will show you. We have a spin coater in the lab. We will show you. Harsh will just mount one sample and rotate it. It's working. It's working on the spin coater. You have tested it, right? Tested today. You tell them also. And dropcast something, PMA, not PMA. Dropcast just DI water or something. Show them that this person. So show them the spin coater we have. So then you can use it. And then deposition is another thing we have in the CRF and another lab where you can